Okay. So let's go back to the phase diagram and the Gibbs energy relationship. So this will be chapter 5. Chapter 5. So phase diagram. Okay. So in the last class, I just showed you briefly about what is the phase. Yeah. And now, also I want to show you one of the example for how to connect the Gibbs energy diagram and the phase diagram. Let's look at that more with many actually different kinds of the phase diagram. Okay, different type of phase diagram. Okay, so let's go back to the one of the simplest phase diagram. So when you have A, B binary system, so typically this is mole fraction of B. Even I don't give this kind of information here in the bottom. At least you know that this is A corner, this is B corner. So this is the mole fraction. It means in this direction, you actually number of moles of the B, mole fraction of B is increasing. In this direction, mole fraction of A is increasing. If this is weight percent or weight fraction, in this direction, your weight percent or weight fraction of the B is increasing. And the other direction is weight fraction of A, and the weight percent of A is increasing in this direction, okay? So at least you have to understand this one. And typically this is the mole fraction. It means within this section, you have 1 mole of component. Total number of mole of the system is 1 mole, okay? So at middle, you mean you have 0.5 moles of A, 0.5 moles of B. That's what we assume, okay? Because total number of moles of system, number of moles of the species in the system is 1 mole. That's molar base. Okay? And then one of the actual phase diagram we saw was like this. Okay? So let's assume this is, for example, FCC solution, and this is liquid solution, and this is temperature basically. Okay? And let's draw the Gibbs energy diagram corresponding to this phase diagram. So let's take T1 temperature here, T2, T3 temperature. Okay? Now, when I ask you, okay, can please draw the Gibbs energy diagram for each temperature, then you have to draw it in this way. So when it is T1 temperature, so Gibbs energy diagram, so this axis is now Gibbs energy. Because if this is the molar Gibbs energy, we can use the small g, for example, Gibbs energy. And this is A and the B, and the unit for the x-axis should be same, so this is the mole fraction of B. Is it okay? Whenever you draw the molar Gibbs energy diagram, the first thing you have to look at is each axis. So pure A corner and the pure B corner. Okay? So when you look at the pure A corner at this temperature T1, A is already liquid state. Because this is melting temperature of A, so A is in the liquid state. And B is also in the liquid state. Okay? So both A and the B have liquid state. So when you now, of course, you don't know exactly where's the location, what's the absolute value of the Gibbs energy of A and the B, but at least A liquid have to have lower Gibbs energy than A solid, because A is in the liquid state. Whenever you have the certain state is the stable, it means that phase is to have most negative Gibbs energy among the older state of the species here. So when you have liquid state, or A is liquid state, it means Gibbs energy of liquid should be lower than at least Gibbs energy of solid, whatever solid phase it is. Okay? So we don't know exactly where is it, but at least what I can say is Gibbs energy of A pure, because this is pure, liquid state should be lower than Gibbs energy of A of FCC solid state. Is this okay? At this? The difference, we don't know. The absolute location, we don't know. But the only thing we can tell is this is lower than this one. Okay? And the other side too. So, I don't know the difference, but this B liquid should be lower than B FCC. So this is okay. And then A and B, if you look at it, FCC is FCC solution, and liquid is liquid solution. So liquid is liquid solution. It means liquid. You have liquid Gibbs energy of liquid solution, and two endpoint of that actual solution is pure A, pure B liquid. Yeah. And between these two, there should be some connection by the Gibbs energy function because it's one solution. Okay. The shape of this liquid, the shape of the Gibbs energy could be, different depending on the interaction between A and B. If A, B like each other, if the activity coefficient of A, B is less than 1, then the Gibbs energy curve between A, B should be very negative. Am I right? The Gibbs energy, you have ideal Gibbs energy, and then that's when the activity coefficient equal to 1 for pure A, pure B, or A and B. And when your actual Gibbs energy is, more negative than ideal case, your activity coefficient is less than 1, and in that case, the curve should be more negative than the ideal case. Yeah? Is it okay? Or, if this is regular solution, so omega is negative parameter, omega AB is negative, it means you should have lower Gibbs energy than the ideal actual Gibbs energy. Okay? So, whatever it is, we don't know, but at least it should connect between the pure A to the pure B. Okay? Solid, same thing. It could be ideal solution or positive or negative actual deviation from the ideal solution. Whatever it is, it should connect to each other. Okay. And as I mentioned, the shape here, it could be even this, it could be even this, or it could be even this, whatever it is, it should be. It should connect to each other from the pure A side to the pure B side, okay? And the only thing you have to be very careful here is, among this entire composition range, liquid Gibbs energy should be lower than solid Gibbs energy. That's the only one condition, because if you look at all this entire composition here at this temperature, liquid is always stable than the solid. There's no solid phase appearing. So when we say, okay, certain phase is appearing, it is only at the given composition. Okay? So, for example, at this composition, I say at this point, liquid is stable. Yeah? Am I right? So when you say thermodynamic equilibrium state, or when you say, okay, this phase is stable than the other phase, there's two conditions. Number one, temperature and the pressure. So you have to know what's the actual final temperature and final pressure of the system. And then you have to know what's the initial composition. Initial composition. Because that will tell you what kind of phase will be formed in the end. Initial composition means mass balance. That initial composition will be dissociate or associate, whatever it is, but the final overall composition should not change because there's no exchange of the mass between the system and surrounding. It's closed system. Yeah? So initial composition and then final temperature and the final pressure is the most important one. Whenever we draw this kind of diagram, typically we don't say anything about pressure. It means it's at constant pressure already. That's what we assume. Okay? The most of material engineering, we assume 1 atm unless we specify some other pressure. Okay? So typically when you draw the diagram like this, if there's no mention about the pressure, it means pressure is constant. It's pressure independent basically. Okay? So you don't have to worry about pressure part. And then the next thing is at the given temperature, because thermodynamic equilibrium is only obtained at the given temperature. You cannot have the equilibrium state of system with the two different temperature. It's at the given temperature, yeah? One temperature. And then, what's the composition? Initial composition or overall composition. Okay? So, at this composition, for example, at this temperature, you have to always check, okay, the Gibbs energy of your phase. Okay, here, liquid is lower than solid, lower than FCC. Liquid is lower than FCC. Liquid is lower than FCC. In entire range, if you draw the Gibbs energy diagram like this, liquid is more stable than solid FCC phase, yeah? So this is liquid. This is FCC solution. So in the end, you can say, okay, in the entire range here, if I just marking what kind of phase can be formed, then you can mark this way. Okay. So entire range here, liquid is stable. So liquid is stable, liquid is stable. Okay? Now, let's look at the other case. Now how about T3? Okay, this is A and the B. Same thing, so this is Gibbs energy. At the T3 temperature, as you can see, A is solid FCC state, and B is also solid FCC state here. So, I don't know exactly, but at least what I can tell here is Gibbs energy of A, FCC, and Gibbs energy of A, liquid. At least FCC should be lower than Gibbs energy of liquid. And why I put the not, it means it's pure, yeah? And then here, same thing, Gibbs energy of B, FCC, and Gibbs energy of B, liquid. Are you good? Now, the shape, I mean, whatever. Okay? And if you look at this one, in the entire composition, and in each composition here, liquid is always, solid is always stable than liquid. FCC and the liquid. So entire range here, I have FCC phase. So when I ask you, okay, in the midterm or final exam, when I ask you, okay, draw the Gibbs energy diagram at the T1 temperature, you have to draw it in this way. And then you have to even mark, okay, what is the phase stable in each composition range. And in this case, from here to here, liquid is stable. That's the marking, okay? And the other one, FCC is stable, okay? Now how about T2 temperature? T2. So this is T equal to T2 temperature. Oh, let's draw it here, because this is something we have to discuss a little bit further. So T equal to T2 temperature. Okay, same thing, A, B, mole fraction of B, Gibbs energy. So if you look at the diagram over there, so at T2 temperature, A is stable as a liquid phase. B is stable as solid FCC state, yeah? So A, is okay? And the B, liquid. So is this okay? And then now we have to draw the line between the A solution or liquid solution and FCC solution, yeah? So liquid solution, okay, and FCC solution, okay? So this is liquid, FCC, okay? So we are doing actually we are repeating exactly the same thing as I explained in the last week. So if you look at just as it is, if you assume that there is only single phase existing in each composition range, okay, most stable phase is only single phase. You don't have two phase, only single phase can exist. Then, at this composition here, my liquid have lower Gibbs energy than my FCC. Am I right? So liquid should be stable. And here, same thing, liquid should be stable in FCC. Liquid should be stable in FCC. And then once you cross this one, now FCC is more stable than liquid. FCC is more stable than liquid. FCC is more stable than liquid. Okay? So it looks like only liquid phase and FCC phase existing here, yeah? That's happened when we assume there's only single phase possibility. Okay? But when you mix the AB together, I mean, if the AB doesn't actually make any solution, you can have pure A, pure B existing together, yeah? So we're going to learn later so-called Gibbs phase rule to tell how many phases can exist maximum at the given system, okay? But according to those kinds of Gibbs phase rule, in the binary system, two-component system, when the pressure is constant, you can have maximum 3 phases can exist together. Maximum 3. Easily 2. And then minimum 1. Okay? So, minimum 1 assumption here is wrong. That's actually really assumption. We could have more than 1 phase can exist together here. Okay? So, in order to actually apply those kind of possibility, then that actually the system can have more than 2 phases exist together. We have to now apply the certain rule, and that is actually so-called common tangent law or common tangent rule. Okay? So when we have this kind of Gibbs energy diagram, because we are in the 2D dimension here, yeah? So at the temperature peaks, the only thing you are changing for the Gibbs energy point of view is the composition. Okay? So when you have any phase, it is solution phase or it is stoichiometric phase, whatever it is, you draw all the possible cotangent line between the two different phases. Okay? So, for example, I want to draw the cotangent line between this one and this one. This liquid, this solution and this solution. I want to draw the cotangent line. So then, you can draw the cotangent line like this. So from here to here, I have cotangent line like this. Okay? So cotangent line means, at this point, okay, at this point, this is the kind of the first derivative line, and this is also first derivative actually the line at this point here. And then they should have exactly same slope, then two lines existing at the same exactly overlap each other. That's the cotangent line. Okay? We draw the tangent line for each one, but both of them have exactly same slope. That's the cotangent line. Okay? And when you draw the cotangent line, why I'm drawing the cotangent line than others is like this. So when you have this cotangent line, so it means I'm connecting this point and this point within this cotangent line. Okay? So within inside of your cotangent point, okay, anywhere on the cotangent line, it means in terms of actual mathematics, if you're in the middle, so for example, let's take this one. So let's take now this composition. At this composition, this liquid phase have lower Gibbs energy than this FCC phase. So in terms of single phase assumption, liquid have negative Gibbs energy than solid. So liquid should be more stable than the solid phase, solid FCC phase with this composition. This composition is not changing. Composition here. And this composition of liquid Gibbs energy is this one. This composition of solid Gibbs energy is this one. So liquid have lower Gibbs energy than the solid phase. Yeah? That's good. However, if you now apply actually a cotangent line here, so if I make somehow my Gibbs energy at this point, it means in order to make this one, I have to take this one for the certain fraction and this one for certain fraction. Then I can make any, so within this line, so any actual point in this line can be taken from this one and this one with a certain fraction. Okay? So if I take, again, sorry. Let's draw this cotangent line blue again. So if I assume my composition is this one, and if I make a certain fraction of liquid and certain fraction of solid at this composition, then my Gibbs energy can be located at this point. Because this Gibbs energy is this one, this Gibbs energy is this one. So if I say, okay, I have 60% of liquid, 40% of solid, probably I can make this composition here, this point. Is it okay? Do you get it? So when you have within any kind of curve here, y and x, if I put these two together, the point here is the fraction of this one plus fraction of this one at this point. Yeah? So that's cotangent point here. So I have these two cotangent points, and if I take a fraction of this one, I can make this Gibbs energy. The fraction, when I take it, is the amount of those phase. So if I take 40% of this phase with this composition, that will give this Gibbs energy here, this Gibbs energy. If I take 6% of this one at this composition, so Gibbs energy is this one, then I can make this one, overall, this composition. Okay? So mass balance is fraction, and sum of these two actual Gibbs energy should be here. Is it okay? Now, if you assume that, so it means if I assume there's two possible phase, so dissociation of my phase into the two phase, then I can create this Gibbs energy, which is lower than my pure liquid Gibbs energy. Single liquid Gibbs energy. Okay? So you can have two phase is more stable than single liquid phase. Okay, then why we are taking the cotangent line? I mean, you can take whatever line you want if you like. So I can, for example, take this point and this point. I mean, you can assume that these two phases can exist. But however, that Gibbs energy is higher than Gibbs energy from the cotangent line. So minimum Gibbs energy is always on the cotangent line. And if you have more than one cotangent line, among those cotangent line, lowest cotangent line combination have lowest Gibbs energy, of course. Is it okay? You get it? I mean, graphically, that makes sense, yeah? So, whatever composition, but if it is inside of these two cotangent points, okay, then liquid plus FCC combination here have a lower Gibbs energy than single liquid or single FCC phase. So inside of here, you have liquid, FCC solution combination. Okay? And then this side, you have liquid. Because liquid single phase have lower Gibbs energy than FCC. But as I mentioned also last time, okay, why not I'm extending this cotangent line here, and cotangent line is lower than liquid phase, single liquid phase. However, if you want to actually extend this cotangent line, you have to first make your mass balance. So if I have this composition, this 2-point combination can make any composition within here, but not in this side. So you cannot extend this cotangent line outside of cotangent point, because it doesn't actually make a mass balance. Okay? So you cannot have cotangent line outside of your cotangent point. Okay? So in here, single liquid phase is more stable than single FCC phase. Okay? So liquid. And then here, same thing, same region. FCC phase will be more stable than single liquid phase. Is that okay? So you have three phases: liquid, liquid plus FCC, and FCC. Okay? Now, one more very important thing. Let me just finish one thing. One more very important thing is, okay, let's assume my composition is this one. Then I have this liquid phase for the certain amount and this solid phase with a certain amount here. And if my composition is now, for example, this one, I still have this liquid phase with a certain fraction, this solid phase with a certain fraction. Okay? The fraction of liquid and solid should be different than the fraction of solid and liquid in the other case. However, the composition of liquid and composition of solid is exactly the same. Because these two cotangent points in x-axis here is the composition of liquid and the solid, which is in equilibrium, which is existing together. So at the middle you have 50-50, at exactly at this composition, 100% of liquid, 100% of solid, and within inside, your amount will be changed depending on the position. However, the composition of liquid and composition of solid existing together within entire this range is still same. Composition is same. Amount is different. Do you get it? Composition is not changing because that's two cotangent points. However, the amount, if I want to make it more this one, if I have more close to this one, I should have more this one than the other one, yeah? If I'm here, I should have this one is 90% and 10% of the other one. In the middle, 50-50. So the composition, the amount of the phase fraction, amount of the two different phases changing. However, the composition of that phase, two solid and liquid phase, composition is not changing. Is it okay? Composition is same. However, the amount is changing from 0 to 100% or 100% to 0 within inside of this cotangent line. You get it? That's very important point. Because now, if you look at this one, if you look at the diagram there, so at that diagram, we say that the diagram we are talking about was this one. And we are talking about this T2 temperature, yeah? So, now if I actually connect this one with this one, so if you look at this one here, at this temperature, up to here, I have liquid phase. Am I right? Here, I have FCC phase. In the middle here, I say two-phase region. So here, in the middle, liquid, FCC phase. Okay? Now, when you look at this one, you have to be now very careful. So these two composition here. So this composition 1, this composition 2. This composition at this point and this point. So it means end of liquid single phase region or end of FC single phase region here. Okay? This one corresponding to the exactly this point 1, exactly this point 2. So we have liquid, FCC, and then liquid plus FCC in the middle. I told you, within inside of this one, the composition of liquid and composition of the FCC is not changing. The fraction is changing, the amount is changed, but the composition of each specific phase is not changing. And that's actually here. So when you read a phase diagram, okay, I have single liquid phase, single FCC phase. In between, I have liquid plus FCC phase. But whatever composition you are taking in this middle of this actual composition, so let's, for example, take this composition, then I have two phase, but my liquid phase is this one, my solid phase is this one. The amount is changing, but the composition of liquid is this one, composition of solid is this one. And that is happening because of this cotangent line. So here we call this one theoretically cotangent line in this kind of diagram, we call this one as a tie line. I mean, the terminology is slightly different, but it's the same meaning. And typically, the tie line is dotted line. It's expressed as dotted line in the phase diagram. So this one, tie line. So tie, I mean, you have tie of the one side to the other side. It's a tie line. Okay? And one side is this point, the other side is this point. When you have in the phase diagram, I mean, sometimes very kind people put all this tie line at dotted line. Then it means it's a two-phase region. The tie line should be parallel to the temperature. It's constant temperature. You cannot have, non-isomer temperature tie line because thermodynamically you cannot have this phase and this phase cannot exist together because it's a different temperature. So tie line is only existing at the given temperature. Okay? And tie line show the two composition of the two phase in equilibrium at the given composition. Okay? So the end point here is the two composition of the two different phase, which is equilibrated at any of the inside of this tie line. Anywhere inside of this tie line. Okay? Very good? And then, when you actually learn tie line, we always learn, so, cotangent line, tie line, okay? And some people say that even this is tie line, that's cotangent line. It's same, because I mean, it's really, if I see this one from the Gibbs point of view, we say it's cotangent line. When we say it's really phase diagram point of view, we say it's tie line. But the idea is same. Its origin is same, basically. Okay? Then, you might be very interested. Okay, so you say the certain fraction of A, certain fraction of B. What is that certain fraction? How we actually calculate that? Okay? That's a so-called Lever rule, or Lever rule. I think you probably heard about Lever rule. So Lever rule is telling you when you have the more than two phase is in equilibrium, so in the binary system, when you have two phase is in equilibrium, what is the fraction of the each phase at the equilibrium state? That can be told from the Lever rule. Lever rule is very simple. It's like a seesaw. It's a seesaw rule, basically. Okay? So when you have, so at the Lever rule, these 2 points, to end point is the two different phase position. So in this case, this is liquid. And in this case, this is FCC. Okay? And then, I mean, if this is seesaw, where's the actually stand of the seesaw? So that stand of seesaw is your original composition. So let's take this is my initial composition. Or you can say that this is overall composition. So overall composition, average composition of the system. What's my input composition? What's my average composition of my output? It's same here because I'm not changing the composition. Mass is not changing. Okay? The fraction of each element, elemental base, it's not changing. So initial composition, if this is closed system, initial composition same as the final composition. But when you say final composition, you might have more than two phase. So then I mean final composition of solid phase and liquid phase is different from the final overall average composition. So it's overall composition or initial input composition of A and B. Okay? So let's assume this is my initial composition. And basically you are just putting that position here as the position here. So this one. So this is my kind of the origin point of my seesaw. So stand of the seesaw is here. Okay? Then you can think about, okay, how much weight I have to have liquid phase and how much weight I have FCC phase. That's lever rule or lever rule. It's a seesaw rule. Okay? So weight of this phase should be this divided by this one, yeah? I mean, if you have the seesaw is more close to this side, but if you stand parallel, you should put more weight here, less weight here. So the difference of the weight is really difference between these two distances. Yeah, it's same as this distance. So liquid phase so phase here is, let's assume this is A, and then this is L, A divided by L. So amount is not really correct one. So fraction, but this is amount, weight base, fraction of liquid should be A, this distance divided by entire distance of your seesaw, L. And then fraction of FCC solution should be P divided by L. Or L minus A divided by L. Is it okay? Now, if I actually apply here, if I apply the same thing at this phase diagram, so this should be A, this should be B, and this should be L, yeah? Okay? Amount of liquid phase is A divided by L. So, the other side, A divided by L. Amount of FCC is the other side, so B divided by entire length L. That's the fraction of the A liquid phase and FCC phase. That's simply lever rule. Okay? So according to the lever rule, you can now tell how much fraction of the phase is existing in the system. So phase diagram tell you already what is phase, and then when it's two phase, what's composition of each phase, and then lever rule say what's the fraction of each phase. Is it okay? So let's take one more example here. So okay, how about let's do real mathematics. Let's take this one, 0.7, 0.25. Okay? So at the T2 temperature, so I have T2 temperature, and my original composition, initial composition, A is 0.5 moles, B is 0.5 moles. Okay? What is my final phase according to the phase diagram? How much is it in each phase? Okay? So at this one, you say, okay, at this two, but my actual composition is 0.5. Okay? So at least from the phase diagram, okay, I have liquid and FCC plus liquid plus FCC. I know it's liquid plus FCC. Is it okay? So when you read the phase diagram, you have to always read it in this way. Okay. So at this point, for example, at this point, always at the given temperature. So phase equilibrium is always at the given temperature. So at this point, so if your composition is 0.1 at this temperature, you look at left side, right side. Boundary of the left side and right side. Left side boundary, okay. It's boundary, I don't know exactly, but it looks like boundary of liquid. Liquid phase. Here, same thing. Look at left side. You have, okay, FCC phase. Right side, I don't know, but I mean, it looks like FCC phase. Then it's FCC. Same thing at this point. Now, look at left side. Okay, here's the liquid. Oh, here's FCC. So it's liquid plus FCC. So always look at your left side, right side. And when you see the phase boundary, read that actual phase and that phase. If this is too different, then it means you have two phase. Is it okay? That's how you actually read actually your phase diagram. Okay? Liquid, FCC. Okay, you have two phase. Two phase. And this is minimum information, yeah? So I say, okay, initial composition is this one. At T2, I have liquid plus FCC. But what's the fraction of each phase and what's the composition of each phase? That's actually what I need. So, composition of liquid phase. Composition of liquid phase. So mole fraction of B is 0.25. So mole fraction of A equal to 0.75. And mole fraction of B equal to 0.25. So this is liquid phase, yeah? So it's composition. FCC, so mole fraction of A equal to, no, B is 0.7, it's 0.3. And mole fraction of B equal to 0.7. Is it okay? So this is phase composition. But I didn't say that how much of this one and how much of this one is existing here. Total number of moles is 1 mole. The fraction of this one, the amount is now, okay, so liquid phase amount is this divided by this length. So 0.7 minus 0.5. And then entire length, 0.7 minus 0.25. Okay, this is fraction. And then N total. And total in this case is 1 mole, yeah? Two together is 1 mole. And this is fraction. So if you want to know the total amount, and total times fraction. Same thing here. So N total times 0.7 minus 0.25. And then from B point of, so FCC point of view, this distance divided by entire distance. So 0.7, 0.5. Okay. Of course, this is x, this is 1 minus x. These two together should be 1. Yeah. So this is the answer I want to have. So when I say, okay, based on the certain phase diagram, and you have this amount of the initial composition, this is initial composition, and this is temperature, final temperature. Find out what is my final phase, and then its amount and the composition. Then you have to actually answer all this one. Okay? This is 1 mole in total, but if I say 2 moles, then you have to, and total is 2. Okay? So you have the different, so total number of moles should be still 2. Okay? Theoretically, Levy rule is applied for the gram base. It's not mole base. Mole is very, sometimes mole is very, very actually confusing. Okay? Because I'll actually explain one case like that later. But theoretically, Levy rule have to apply only for the molar base, only for the weight base, not the molar base. Okay? I'll show you one case like that later, okay? You good? At least you understand? So if you understand this one, everything else is very, very simple. You get it? So now, let's move to the next example. Question.
It's just explained.
Explained already, okay, good. So minute term number 2, May 30th, okay? So how about this one? Now, let's go back actually, a little bit more simpler case again. Okay, A, B. This kind of diagram. I mean, it's in some sense, it's more simpler than the previous one. Okay, so here I have liquid phase. Okay, I mean at least above the certain temperature, it should be liquid. So this is melting temperature of A, melting temperature of B, and then I give this is liquid. Okay, A, B doesn't make a solid solution in this case. It's not FCC solution, BC solution, just A, just B. A, B is not mixing each other. That's what it means, yeah? Doesn't make any chemical solution. Okay, so now at this point, what kind of phase I have? Left side, what phase I have? So this side, A solid, this side, liquid. So this is A solid plus liquid. Entire this range, same, yeah? You good? You have to know how to read the phase diagram. Otherwise, forget about your midterm and the final exam. Okay? This one, left side, right side, B solid, yeah? I mean, the order, you can change it if you like. I mean, it doesn't matter. B solid plus liquid or liquid plus B solid, okay? I just do it because I always read left and right, but it doesn't matter, whatever you like. You good? Now, here, left side, A solid, B solid. Unless I say A, B is the same solution, then you have one side, the other side, A solid, B solid. You good? How about this one? A solid, liquid. And this one, liquid, B solid. In fact, actually, entire this range, you have A, B plus liquid. A solid plus B solid plus liquid. That's your tactic point. I'll explain this one later. Okay? So you have at least, you have to, when I actually give the minimum information with the phase diagram, and then I say, okay, there's the this kind of phase is existing. Then you have to now put down the what kind of phase assembly is existing in each area of the phase diagram. Okay? Your final exam, one of the questions is like this. I'll give you a little bit relatively complex phase diagram and give you minimum information about what phase can exist in the system. And then you have to start to put all the name, all the phase name for each area. Okay? You good? So that's why how to read, you have to know how to read the phase diagram. Okay, now let's draw the phase diagram. T1, so simplest one. T2, T3. T1 and T3 is very simple. So T1 temperature, A is solid state, B is solid state, yeah? So Gibbs energy of A, solid, Gibbs energy of B, solid. And okay, so at least you can present 4 points in the diagram like this. As I mentioned, this location, we don't know exactly. Absolute position, we don't know. Okay? And the only thing you have to make sure that is, this should be lower than this one, this should be lower than this one. That's the only two. You have to be very careful. And then, now, Gibbs energy of liquid phase. Okay? Gibbs energy of solid phase, A and D, because there's no solution. Okay? So this is just Gibbs energy of A solid. I say solid, but it may be, for example, this is FCC, this is BCC, two different crystallographic structure. So there's no solubility in each other. Then you have just single Gibbs energy point here, single Gibbs energy point there. And some people try to say that, okay, Gibbs energy like this, Gibbs energy like this, it doesn't matter. I mean, this this is, just arbitrarily thing. You can just even say that, okay, this is point Gibbs energy, because there's no solubility of other thing. Theoretically, they could be very small, so that's why people try to draw a little bit line. Doesn't matter. That doesn't change anything here. Okay, now, is there any common tangent line here? No. Common tangent line is any connection of two different phase, Gibbs energy of two different phase with the same tangent line, yeah? So, this is one common tangent line, yeah? A and B. A have any kind of slope, B have any kind of slope of tangent line, and the only tangent line which can connect together is this one. Is it okay? This is one of the common tangent line. And this is another common tangent line between A and this liquid phase. Yeah? This is liquid. Am I right? And you can have also the other common tangent line if you like. This is liquid plus B solid common tangent line. Now we have three phases, so you can have at least three possible combinations of the common tangent line. Yeah? Among them, in any composition here, among them, this bottom one, A solid to B solid, is lowest common tangent line. So this is most stable common tangent line. Okay? So, when you have here, I cannot have, so if you talk about single phase, liquid is always stable, entire range, except for the pure A, pure B. Yeah? However, because there's common tangent line, we have to consider possibility for two phase existence. And so when you have solid A, solid B existing together, so this one, okay, so solid, have lowest Gibbs energy combination in entire range. Is it okay? So when you draw the Gibbs energy diagram, this is okay. But when you draw a Gibbs energy diagram, for example, like this, okay, so let's say I have GA solid, GB solid, and GB liquid, GA liquid, and then okay, I have liquid is like this, and then if you say entire range here is the A solid plus B solid. This doesn't make sense here. I mean, whatever you actually draw, this common tangent line, below this one, liquid is more stable than this common tangent line. So this phase notation and the diagram doesn't match each other. This is wrong. This is completely wrong, yeah? So at least when you draw this liquid line, you have to make sure that this is higher than your AB common tangent line to make sure that you have A solid, B liquid, and B solid is existing together here. Make sense? So you draw whatever line, but at least topologically you have to make sure that you are not actually obeyed actually this minimum Gibbs energy concept. Okay? Is it good? Oh, gap behind. Is it okay? Good? Understand? Okay. Gap. What's your name? Can you come? Come out. It's fun now. Fun time. Okay, I'll draw actually the easy one, T3, and you draw the T2. Come. Okay, this is one for you. I'll draw the T3. Oh, you can draw it here. So if you like, I can give you even. Okay, this is A, B, Gibbs energy. When T equal to T2. Okay, T equal to T3, while he's doing it, I'll show you. T equal to T3, liquid is more stable. Pure A is liquid, pure B is liquid. Okay, so you draw it. So, yeah, whatever it is. So this entire range you good? So let's watch him how to draw the T2. So all of you think about it while he's doing it. Think about it. Good. 95%. 95%. It almost makes sense. However, there's some critical problem here. The cotangent line is not cotangent line, yeah? The cotangent line is not cotangent line, yeah? Okay, you understand? So, when you actually draw this kind of diagram, a lot of students actually make a mistake like this. Okay, you know the answer, but you have to draw the proper cotangent line, yeah? So he knows exactly what you want to do. So for both A and B at T2, A and B, A is solid state, B is solid state too, yeah? So when you draw this kind of diagram, you have to know exactly what you are doing before, then it's very easy to draw it. So if you just put all this one first and then if you want to do it, a little bit difficult. But if you are actually doing this, okay, I have this cotangent point like this. So for example, let's take, this is x1, this composition is x2, okay, then this should be x1, x2, and then you have to draw the something which make this cotangent line. Yeah. So here you can put actually your GA solid. That's easiest. So this is GA solid. I mean, you don't have to make like very precisely, but at least you should make it reasonably. Okay? Not like this one and say this is the cotangent line. Obviously, this is not cotangent line. Yeah? Okay? So this is inside here. So liquid, here to here, A solid plus liquid, liquid plus B solid. Is good? Within this area, the cotangent line is lower than liquid, so it's liquid plus B. Same thing. Within this one, liquid phase is higher than cotangent line between A solid and liquid. So two phase instead of single phase. Here, there's no cotangent line here. I mean, this one is not cotangent line, yeah? There's no two phase. I mean, this is cotangent line, but that cotangent line is much higher than my single liquid phase cotangent line. Okay? So, liquid phase is stable here. Good? Okay, now let's move on. These two conditions. Mask. So I'll give you easy one. This is easy or difficult? T2. So, if you like, you can draw it here. So first, put all the phase name in each area. So here, what's this one? Are you sure? Are you sure? So, this point, you are reading left side, right side. Left side A solid, right side liquid, yeah? So all this one is liquid, yeah? That's correct. and this point. Left side, liquid. Right side, AB. Yeah? It okay? So inside this one, inside all this area is liquid plus AB, yeah? And here, left side. Liquid plus AB, yeah. AB plus liquid. All of you, is it okay? Left side, right side. And this one, B plus liquid, yeah? And here, B solid, left side, AB, yeah. B solid, this one, plus AB, yeah. And this one is single AB, single A, single B. Okay? So, now diagram. Don't leave. He left. You have solid and solid have connection here.
AB에 대한 식을 써야 될까요?
AB가 거기 있니? AB composition이 어디 있는데? Yeah. So only in the middle point, yeah? Where's the AB point? Yeah. You're connecting solid to solid? It's not the same solid? It's not solution yet. 해봐라. Good. Enough. Thank you. This is already good. It's difficult. Yeah. If you first look at this one, I mean, it's very difficult to how to do it. The answer is this one. When you have A, B, so you have A solid, B liquid, A solid, A liquid, A solid is stable, yeah? From the B side, B solid is stable, then B liquid, yeah? And then you have liquid Gibbs energy, and then you have AB Gibbs energy, solid, AB liquid. There's no AB liquid. AB liquid is part of the entire liquid phase, yeah? There's no AB liquid, okay? So AB liquid is part of the entire liquid. And you have AB solid phase, so AB solid should be somewhere existing here. And for the AB solid point, at least it should be lower than Gibbs energy of liquid point at that composition, yeah? AB solid is stable than liquid, okay? So at 0.5, this one, this is number 3 basically, composition number 3. At 0.5, you have Gibbs energy of AB solid, which is lower than the Gibbs energy of liquid. So at 0.5, at least solid AB is lower than Gibbs energy of liquid itself. Okay? So solid AB is stable. Okay? And then now here on this one, you have tangent line. So this means it's tangent line, cotangent line between A and liquid. This means cotangent line between liquid and AB. Okay? So your liquid Gibbs energy somehow passing in between these 2 points make a 2 cotangent line inside. Okay? And then here you have cotangent line between AB and the B solid. So AB and the B solid. That cotangent line should be lower than any other cotangent line or single phase line. Okay? So this is the solution here. So in this case, you know the phase diagram, so you have to really make your diagram based on the phase diagram instead of making this one to compare it. It's very difficult. So you just draw it. Okay, where's the 1, 2, 3 composition? Okay, this is basically composition 1. This is composition 2. Composition 3. You know reasonably where it should be. And then you just put your AB point, and then A point and the B point, and then draw the liquidus line in the middle by yourself to make 2 common tangent line inside here. That's the easiest way. Okay? So, if you have like this, here you have single liquid phase region. This one is common tangent line between A and the liquid phase, and the single phase, and then these 2